Okay, students, we now have the 7th lecture on consolidation settlement. During the course of the last 6 lectures, we had made considerable progress. We had discussed almost threadbare the phenomenon of consolidation, and we had seen how to compute several parameters which are used for expressing compressibility. We had understood the method that is being used, the so called odometer test, for determining the void ratio changes and to determine the parameters which are important for us from point of view of understanding the phenomenon of consolidation. As we had seen, we had seen two methods for, very broadly speaking, methods for determining the total compression and method for determining the time rate of compression. We had also seen one or two examples. We saw in the last lecture, in the lecture that just preceded, how to compute the coefficient of consolidation from an odometer test. Let us take a quick review of this so that we can put in perspective, the correct perspective, what is going to follow in today's lecture. Let us see the next slide. So, as I said, this is what we had a look at in the last lecture. That is, we saw what isochrones were, what is the variation of excess hydrostatic pressure with respect to Z and T in non-dimensional terms, and we saw that there are two values of capital T which are of prime importance. We saw what is average degree of consolidation and how it varies with time. We saw this lookup table, a very useful lookup table where we have discrete values rather than a curve of TV corresponding to U, and as I mentioned, given U, we will be able to calculate capital T and therefore small t in any given instance. That is, given, or rather for a stipulated value of degree of consolidation, we can find out what will be the probable time that will be taken, or given a certain duration or time of performance of a building, we can find out over that period of time how the consolidation process would have improved or progressed. Okay. There were two other expressions convenient for computing capital U rather than the complicated expression that we had derived from one dimensional compression theory. We can use these expressions, although they are not rigorously valid. Then we found that CV can be determined from the odometer test results either by the square root of time fitting method or by the logarithm of time fitting method. Both are basically curve fitting techniques. The first square root of time fitting method, we use the condition that the straight line here starting from the 0 consolidation point and going tangentially to the curve of dial gauge reading versus root of time will have certain ordinates, and if we draw another line which is a tangent to this red line, which will have may not necessarily be a tangent. If we draw another line which has got ordinates equal to 1.15 times x, then this point here where it intersects this red line, that corresponds to d90 and root of t90, from which we can now calculate the value of CV by knowing that capital T90 equal to 0.848. Similarly, from this logarithm of time fitting curve, we first determine ds, the starting point, that is u equal to 0 point, by taking advantage of the fact that this curve is a parabola. So, we set out with 2 points A and B, a distance y, another distance y, so that we can locate this point corresponding to ds. Once we know ds, that is u equal to 0 and u equal to 100, the midpoint gives you d 50 and therefore T 50 and therefore CV on the basis of capital T 50, which is 0.197. We also saw another phenomenon known as the pre-consolidation phenomenon, that is some soils which have undergone compression under larger loads than are existing today will show the phenomenon of over consolidation, that is they will rather follow the recompression and curve beyond that recompression, and this point corresponding to the maximum pressure to which a soil has been subjected to in the past can be obtained by a graphical procedure which involves construction of this tangent through the point of maximum curvature, drawing of a horizontal line and then a bisector, and then extending the straight line portion BC to meet the bisector at P. The pressure corresponding to P gives you P max. Now, in this lecture we will continue to see some more examples, then we will pass on to another important phenomenon known as the secondary consolidation, and then lastly radial consolidation. Let us see a few examples. If you remember, we had seen one example, the example number 4 it was in the previous lecture. For convenience, I repeat the statement of that example again now. Let us see. A 6 meter thick clay layer is subjected to a load of 60 kilonewtons per meter square. 1 year after loading, average consolidation is 50% complete. Okay. So, in this problem, when we saw this earlier in the previous lecture, based on the same data, we computed CV and we also computed the settlement at the end of 1 year. You probably remember that we calculated the total settlement based on MV, and since we know that at the end of 1 year 50% consolidation is completed, we calculated settlement at the end of 1 year as 50% of the total settlement. Now, in this problem as a continuation, we shall see some interesting calculation. What we now see is how to compute the rate at which water is flowing out of this soil at the end of 1 year. We know that this phenomenon of consolidation goes on taking place at a slower and slower rate. Initially it takes place at a very fast rate. Initially water is expelled out at a very fast rate, but that rate goes on decreasing as more and more water goes out, and as less and less water is remaining to be expelled, and since the water pressure is also getting dissipated, the excess hydrostatic pressure is getting dissipated, water starts moving out relatively slowly, and with time the rate at which water flows out goes on decreasing. So, it will be of interest to know at the end of 1 year, when half the consolidation is completed in this case, at what rate is water still flowing. So, the question is determine the rate of outflow of water per unit area from the surface, because this clay layer is a large huge layer. We are more interested in an idea of the flow. So, we like to calculate the flow per unit area. So, the solution is, we will start with what we already know. We have already solved this problem, and so we already know that the settlement corresponding to 50% consolidation and 1 year is 0.3045 meters. This we had computed earlier. Now, we know that this is less than 60%, and therefore, we can use this formula TV equal to pi by 4 u square, and we can incidentally compare this with an expression involving small t, and we can see that since capital T is a constant into degree of consolidation square, that is nothing but this parabola, then T can also be expressed as a constant A into the amount of settlement that has taken place at this T up to this point of time. So, T V equal to pi by 4 u square can be taken to be similar or identical to T equal to A square. All that remains to be seen is what is A. If we know A, then we know that this will strictly or exactly correspond to this expression. So, let us see, since A is nothing but T upon A square, at least one value of A can be determined from the available data already. That is, we know that when T is 1, we have just now computed that the settlement is 0.3045. So, T upon A square is 10.82. This is the value of the constant A which relates T with A square. Now, since we have an expression for T in terms of A square through a known constant A, we can differentiate that and find out at what rate the settlement is taking place. As we know, the rate at which the settlement is taking place will be related to the rate at which the water is flowing out. So, ds by dt, when you differentiate this, will be nothing but 1 upon 2 as, and since t is equal to 1 year, at the end of t equal to 1 year, ds by dt will be 1 divided by 2 into 10.8 into this settlement of 0.3045, which will come here. So, the rate is 0.152 meter per year. So, at this rate, at the end of 1 year, the water is getting expelled. Now, if we assume that water is flowing in two directions, that is towards the top and towards the bottom, that is the so called two-way drainage system, where this clay layer is sandwiched between two pervious layers, then since this is the rate at which the settlement is taking place, this should be resulting because of half the water flowing out through one surface and half the water flowing out through the other surface. So, the rate at which the water will flow out will be half the rate at which the settlement is taking place. So, it will be 0.076 meter cube per year per unit area. This is the answer, and this rate indicates how the compression is going to proceed with time in the subsequent period. If we had known the rate at which water is flowing out or the settlement is taking place at the beginning of the phenomenon, and if we now compare this with that, we would know how the settlement process has slowed down, whether it has slowed down considerably or not, and that will give us an idea as to whether it is progressing satisfactorily or not. If it is progressing very slowly compared to what we had computed, perhaps there is some practical problem associated with this and a situation that needs attention. Now, we will take one more example. This example statement is necessarily rather long, so I will read it out slowly. Let us take a look at this slide. There is a soil profile and it consists of a clay layer. For convenience, I have said that it is sandwiched between two layers of sand, that means double drainage situation exists. Here the water table is at the top of the upper layer. So, the entire system is saturated. A large tank is being now built on top of the layer, the sand layer, and it amounted to an application of a uniform pressure increment of 200 kilonewton per meter square on the clay layer, and it is a rapid application. Now, at the end of 1 year, the excess pore pressure measured with the help of some instruments was distributed as shown in a figure which will follow in the next slide. So, what is asked is estimate the time required for 90% consolidation. So, this problem means that there is a clay layer bound between two sand layers, and water is therefore expelled in both directions, and on this there is a tank being constructed which is responsible for applying a uniform pressure intensity of 200 kilonewtons per meter square, and under this pressure excess pore pressure gets generated, and what is given in the figure that is going to follow is how this excess pore pressure is varying with depth at t equal to 1 year. At the end of 1 year, what is the variation of this excess pore pressure. So, from this graph we will know how much pressure is still remaining, how much pressure has been dissipated, and from that we will be able to have an idea as to how much time has taken for what amount of consolidation. That is, suppose x amount of consolidation has taken place in t equal to 1 year, then we will know that that required a time of 1 year. Then we can find out for 90% what will be the time required, because we will know at this point of time how much pore pressure is still remaining to be dissipated. So, let us take a look at the pore pressure dissipation, pore pressure distribution. This is the curve showing the pore pressure distribution. This is depth, this is the excess hydrostatic pressure, and this is the curve of distribution. So, what we see here from left to right up to this curve, these values, these are the values which represent the remaining excess hydrostatic pressure. We know that in our theory of one dimensional consolidation, for solving the problem of one dimensional consolidation, we had assumed at t equal to 0, u is equal to ui, uniform pressure distribution with depth. It is not really an assumption, it is quite valid at the instant t equal to 0. As soon as we apply the load, since the solids are incompressible, the water takes over. It does take the load, and that means the excess hydrostatic pressure u is equal to a value ui, and it is the same throughout the depth. However, since the ends of the clay layer are connected to the atmosphere, there the gradient is close to infinity and the pore pressure gets dissipated instantaneously. So, now the pore pressure that is dissipated so far is on the right side of this curve, because this total area must represent the area corresponding to u equal to ui. This should correspond to u equal to ui. This is the value of u that is existing now, and whatever value is here up to this between ui and this, that represents the value of excess hydrostatic pressure that has already been dissipated. So, what is the solution? So, solution is we have to find out time taken for 90% consolidation, that is what is T90, that is what we need to find out. It can be very comfortably done in this specific instance by simply studying, if you take a look at the picture again, what is the area occupied by the initial excess hydrostatic pressure curve, because the initial excess hydrostatic pressure curve, though it is not shown here, would have been like this. This would have been the initial excess hydrostatic pressure, whereas now the hydrostatic pressure has reduced to this blue line. That means, between these two there is an area which represents the area corresponding to pressure that has been dissipated, which, in other words, the area under the curve here is indicative of the excess pore pressure that is either remaining or has been dissipated. So, let us see, by considering the area under the excess pore pressure distribution diagram in terms of the number of squares into which we have divided the diagram, we can find out at t equal to 1 year, to which this figure corresponds, what part of this area it is under this curve out of the total area. That is, what is the area occupied by this curve as a fraction of the total area occupied by the u equal to ui curve. That will indicate the degree of consolidation, actually the area which is between the two lines, this red line and the blue line is the one which represents the degree of consolidation in terms of the pore pressure that has been dissipated, or in terms of the area lying between the two curves. So, if you count the squares, the small squares between the two curves, then that will give us the degree of consolidation that has already taken place, and that is number of squares in this previous curve. If you count this number of squares, you will find that this is very close to 11, and that means the number of squares 11 divided by the total 25 will tell you that 0.44 is the degree of consolidation that exists at the end of 1 year. Now, since this is less than 50%, we can use the approximate formula connecting T and 4, I am sorry, T and U, that is T equal to pi by 4 U square, and from this we can calculate capital T as 0.152. So, what does this mean? This means that at the end of T equal to 1 year, from the pressure distribution diagram we find that the area of the portion where pressure has been dissipated is 0.44, which means that is the degree of consolidation, and corresponding to that the capital T value is 0.152. Now, that means we know a value of capital T, we know that corresponding small t is 1, we know that the system is a double draining system, and the thickness of the clay layer, if we know, then we can calculate CV. What we actually need is the time corresponding to 90% consolidation, and what we have is capital T corresponding to 44% consolidation. So, what we will do is we will apply this expression in 2 stages. First, we will apply this expression for capital T equal to 0.152 and small t equal to 1 year, and find out what is h square upon CV, and then we shall use this value of h square upon CV and 0.848 in place of T 90 to find out the time taken small t for 90% consolidation. So, the solution is very simple. At t equal to 1, it must be equal to capital T into h square by CV. So, that is 0.152 h square by CV, or h square by CV is 1 upon 0.152. Substitute that in this and get the value of small t 90, and it works out to 6 years approximately. That means, this particular structure is going to undergo consolidation for 6 long years. Is 90% of the consolidation is going to occur in 6 years time period. So, it is a very interesting way of calculating the amount of consolidation that has taken place, the amount of consolidation that is remaining, and the corresponding time, and whether compared to the lifespan of the building what this value is. If now what it shows is for 90% consolidation time taken is 6 years, whereas for 44% of the consolidation time taken was only 1 year. So, after 1 year the consolidation has been progressing rather slowly, gradually, and at this rate it might take quite a bit of time, maybe 15 years, maybe 12 years, maybe 10 years for the total consolidation to be completed, and in practical terms, and that means if the lifespan of the building is about 40 years or 50 years, almost 20% of the lifetime of the building is going to be the period over which the building or the structure is going to experience the effect of consolidation. After that, when the consolidation process comes to an end, the building will remain more or less free from the effect of consolidation. Now, we come to the second aspect of this lecture, that is secondary consolidation. The consolidation that we have been discussing in the past 6 lectures is known as primary consolidation. It's primary consolidation. The reason why it is called primary consolidation is that is the consolidation that primarily takes place when a load is applied to a saturated clay layer, and we have seen all aspects of this. Load is applied gradually, water flows out gradually, total compression takes place theoretically in infinite time. The rate of compression can be computed using the theory of one dimensional consolidation, and the rate of compression goes on changing with time. Usually the rate decreases with time. It is possible to evaluate how much time 90% consolidation is going to take place. Now, all this consolidation that we have been talking about is purely due to the so called hydrodynamic lag. That is, water is going out slowly, there is a lag between the application of the load and the movement of the water and the corresponding settlement, and therefore, that is known as hydrodynamic lag, and this compression that is taking place primarily due to this phenomenon is known as primary consolidation. Now, this primary consolidation gets over for any given load increment. Primary consolidation gets over for all practical purposes, let us say in a few days. Then starts a secondary phenomenon. The secondary phenomenon is a slightly different phenomenon. It is known as the plastic lag phenomenon. Here a different kind of activity takes place, that is, the particles have now adjusted themselves to the extent possible due to the movement of the water. The stress has already been transferred to them. The entire stress applied onto the clay layer has now been transferred to the solids in terms of effective stress at the end of primary consolidation. And now it is observed that these solids still undergo gradual compression, and this gradual compression due to the movement of the particles, further movement of the particles as a function of time, leads to compression, for continuing compression of the voids, and that is known as secondary consolidation. That is, after the primary consolidation is over, the particles continue to still move gradually under constant stress to find final resting places for themselves, and during this period the voids continue to compress, and that is secondary consolidation, and this is known as the plastic lag, because the phenomenon concerning the movement of these particles under constant effective stress is a plasticity phenomenon. So, the compression that we had discussed in very great detail all this time is known as the primary consolidation, and it is due to hydrodynamic lag, and the compression that takes place beyond the primary at constant effective stress due to plastic lag is known as the secondary consolidation. So, you can see here that there are a number of dial gauge readings shown. This is the same graph which we have used earlier while calculating CV or studying the method for calculating CV. Now, you see here the dial gauge reading versus root of time graph is starting at D0. This is the dial gauge reading corresponding to application of load, but on application of load there is a compression of gases that takes place, and the load gets seated properly. The dial gauge reading corresponding to that state is ds, and now starts the compression arising out of the hydrodynamic lag, and it goes on until we reach the D90 point. If we allow this phenomenon to continue, we will end up with, after a few days, say sometimes 24 hours, sometimes 48 hours, we will find that the dial gauge readings reach a very steady value, and that can be for all practical purposes taken as corresponding to 100% point of primary consolidation. D100 corresponding to primary consolidation may be taken as this point. Now, at this stage, if we continue to watch the dial gauge readings, we will find that it does not stop here, it goes on increasing still with time because of the plastic lag phenomenon at constant stress, and it reaches a real final value df after considerable amount of time, and it is this portion D100 to df which corresponds to secondary compression or secondary consolidation. This phenomenon of secondary consolidation starts at the end of the primary consolidation, and as can be seen in this figure, df corresponds to the point of secondary consolidation completion. So, starting from ds, which corresponds to 0% consolidation, we have 90% taking place up to this, the remaining 10% taking place up to this, and then the plastic lag taking over and the final compression ending up here. It is possible to estimate the total compression starting all the way from ds to df, and then express this primary consolidation as a proportion of this total consolidation for any given load increment. We are assuming that all these dial gauge readings and versus time, which is plotted here in this graph, is for some load increment, and therefore, corresponding to that load increment, how much is the primary consolidation, what part of the total consolidation is the primary consolidation, that can be computed in terms of the dial gauge readings and the change in void ratios. So, the dial gauge reading is ds to d100, that represents the primary consolidation, whereas d100 to df represents the secondary compression, and if df usually is taken after about a day after this 100% consolidation can be considered to be over. That is, after the dial gauge readings have become practically stable, constant, we take that as the point corresponding to d100 and then wait for about 24 hours, and whatever marginal changes that might have occurred during that period would lead to df. So, based on this, if we simply take the ratio of ds minus d100 to d0 minus df, where d0 is the point of application of the load and df is the point of transfer of the load completely to the solid grains, including the portion corresponding to plastic adjustment. This is known as the primary compression ratio. Now, if we are using a method like this square root of time method, in which we get d90 rather than d100 precisely, because that method helps us to calculate d90 rather than d100, whereas the logarithm of time method gives us d100. This d90 once we know, then ds minus d90 multiplied by 10 upon 9 will give us the 100% primary consolidation, and that divided by again d0 minus df would give you the primary compression ratio. The secondary consolidation phenomenon also can be mathematically expressed. It is usually a logarithmic phenomenon because it is a plastic deformation that takes place in the solid grains after the application of the load and at constant load, and generally therefore, it is expressed in terms of a logarithmic equation. Now, we pass on to 3-dimensional consolidation. Actually, it is strange because actually consolidation is a 3-dimensional process, but we started with the simpler version, that is 1-dimensional consolidation, by making simplifying assumptions and idealizations, because that is what is really generally necessary in practice in very large, under very large loaded areas. But there are instances where 3-dimensional consolidation becomes very, very relevant, very important. See, there is a method by which we can accelerate this consolidation phenomenon. After all, on what does this consolidation phenomenon depend? The consolidation phenomenon, its success, its progress, the rate at which it progresses, all these things depend upon the rate at which water is flowing out, that is drainage. So, if there is some way to improve the drainage in any given location, we can improve the consolidation process, we can accelerate the consolidation process, and there it is convenient to use a technique known as sand drains, and we will be seeing some description of that shortly in today's lecture and more details in the next lecture. This technique, as you will be seeing, leads to a phenomenon where compression or consolidation due to flow of water takes place not only in the vertical direction, but also because of the radial flow of water. We provide drains inside the soil which will serve as points towards which the water can flow, and that will induce movement of water into the drains in the horizontal directions as well, and the resulting consolidation however, compression however will be vertical, and in a way this becomes a 3-dimensional phenomenon, and it needs to be analyzed very differently from the way the primary consolidation is analyzed and understood. Let us see the next slide. You will find here a typical soil element once again, and I have shown here the flow of water in all 3 directions. See, if I take x direction, Vx is the flow of water per unit time over this area dy dz, quantity of flow per unit time because velocity represents quantity of flow per unit time per unit area, and this is the outflow per unit time per unit area in the x direction. This kind of expression, this way of expressing the inflow and outflow we had used also while studying the 1-dimensional flow. All that we have done now is to extend that to all 3 dimensions. So, if in the x direction, if Vx is the inflow, Vx plus Vx into rate of change of Vx in the x direction into the distance dx over which the change is taking place, this distance, that becomes the outflow. So, now if you take y direction, Vy is the inflow, Vy plus this into dy becomes the outflow, and for the z direction this is inflow and this is the outflow. So, now the flow equation very similar to the 1-dimensional consolidation flow will lead to once again an expression in which there is a volumetric compression, and the rate at which that volumetric compression takes place will be or can be related to the total quantity of outflow and the rate at which the total outflow takes place. It is possible to extend the equation that we had used earlier to the 3-dimensional system, and as a result of that we can once again get differential equations of consolidation. We had derived in great detail, we had seen in fact the details of the derivation of the consolidation equation del Cv delta u by del z square equal to del u by del t. This is the so called consolidation equation or the diffusion equation for 1-dimensional phenomenon, and we solved this using the theory of differential equations and got expressions for excess hydrostatic pressure. Now, a similar set of equations can be derived, and this can be solved using appropriate boundary conditions, and we can arrive at similar differential equations of motion and corresponding solutions in which average degree of consolidation will be related to the time factor t. The differential equations for consolidation however will be now not only for vertical flow, but also for the other directions of flow. So, suppose we use polar coordinates rather than Cartesian coordinates. Suppose we use polar coordinates rather than Cartesian coordinates, then instead of x, y and z directions we will have a typical element here like this. Suppose I draw it in real polar terms rather than x, y element, we will be having an element like this in which there will be flow in this direction and flow in this direction. So, if I add to this the z dimension, then it becomes a truly 3-dimensional phenomenon. Well, what this means is our 3-dimensional problem in terms of polar coordinates can be treated as a vertical compression problem corresponding to the same z coordinate as in the Cartesian system, plus a consolidation which is now a function of the radial direction, which is a function of the radial coordinate r. So, let us take a look at the corresponding differential equations that we will obtain if we follow the same procedure that we used for deriving this equation for primary consolidation. Following the same steps, we will get two equations for 3-dimensional consolidation, and they will be one, this. We will find that this is in no way different from the equation that we had derived for 1-dimensional compression. All the difference that we have made is we have added a notation Z here to indicate that this is vertical direction, CV for vertical or Z direction, in order to distinguish this from the value of CV that we will get when for the differential equation involving the compression in the radial direction. So, we have two CV values and two equations. These are the ones which need to be now solved in order to get the results of degree of consolidation and its relation to the time factor capital T. Next, if we see this slide, we will come across, in fact, we are seeing what we are seeing here is a method to solve the equation in order to get the values of u, uz and ur. I will not go into the details of the derivation of the relationships between u, uz, ur. Suffice it to say that if I have a relationship between uz and tz or tv, and if I have a relationship between ur and tr, I should be in a position to get the average degree of consolidation for this total phenomenon of 3-dimensional compression, both vertical and radial. This has been done using again the product of variables concept, that is 1 minus the total degree of consolidation is taken as 1 minus the degree of consolidation in the vertical direction multiplied by 1 minus the degree of consolidation in the radial direction. Now, uz is a function of Tv, and we already know that it is CVT by h square. If we can determine CVz, then there is no difficulty at all in getting capital TV. On the other hand, the degree of consolidation in the radial direction, which is a function of TR, that is time factor for the radial process, can be expressed to yield TR as CVR T divided by a factor 2R square, which corresponds to h square of the vertical case. In order to have similarity, the time factor for vertical case and the time factor for the radial case are expressed by similar equations. The term 2R in the radial case corresponds to the term h, that is drainage path. So, we can find out what the meaning of this radius capital R is once we come to the phenomenon of sand drains and their application to accelerate consolidation. Right now, as a prelude to that, we are simply seeing how 3-dimensional consolidation can be split up into consolidation in the vertical direction and consolidation in the radial direction, and they can be put together to get time factor for the vertical direction and time factor for the radial direction. Now, if we know how to determine the time factor for the vertical and the radial directions, we can get the degrees of consolidation for the vertical and radial direction, from which we can get the total degree of 3-dimensional consolidation. Okay. Let us see the next one. In order to see what should be this value of capital R, we have to see two possibilities. There are two ways in which this 3-dimensional consolidation can take place. Suppose there is a certain load that is resting on the soil. This is the soil, and suppose there is a loaded area and this is some load resting on the soil. Then, depending upon the relative flexibility of this loaded area and the soil, that is compared to the soil, whether this loaded area is flexible or rigid, will determine how the consolidation phenomenon is going to take place, whether it is going to take place under the so called free strain condition or under the fixed or rather equal strain condition. That is, if this loaded area is flexible, then we know that the strain of this is going to take place freely. If on the other hand it is rigid, the strain induced in the soil will all be equal under the loaded area at all points. And based on these two extremes, solutions have been evolved, on the basis of which we can calculate capital R for obtaining the value of TR and UR for radial consolidation. As in the case of vertical consolidation, this R is nothing but a length. It is equivalent of the drainage path H, and therefore, it is also a length, and this length will depend upon how these sand drains are arranged. So, now assuming that we can solve this problem of 3-dimensional consolidation either under the so called free strain condition or the equal strain condition, for which solutions have been given by various people, we can see how this can be applied to radial consolidation using sand drains. So, here is a very typical setup that is used together with vertical drains in order to accelerate consolidation. Now, this needs some explanation. See, there are many instances in practice where we will be building rather critical structures which cannot be allowed to experience significant consolidation during their lifetime. Even an ordinary residential building, if it undergoes severe consolidation during its lifetime, it is bound to suffer difficulties. Now, more than that, or more critical than these residential buildings could be, let us say, buildings in factories, structures in factories, huge tanks which contain intermediate products during a chemical process, tanks in which raw material is stored, maybe cement, maybe petrol, maybe any chemical. These usually have pipelines serving as inlets and outlets which are connected to these. Imagine a tank like this connected to a number of other systems through pipelines undergoing consolidation. If this undergoes consolidation during its lifetime, and that if that consolidation is a significant consolidation, then imagine their effect on these pipelines and imagine the effect of these on the adjoining structures. It does not need much explanation to see that this kind of consolidation. So, imagine the effect of this kind of consolidation on the pipes to which they are connected and their effect on the other structures. It is very easy to visualize that as this tank settles, if the settlement is exorbitant, there could be a rupturing of these pipes. If these pipes are carrying dangerous chemicals, then rupture of these pipes could lead to disasters. And therefore, for many critical structures, it is preferable to consolidate the soil before the structures are built by applying a load similar to what these structures are going to cause when they are constructed. Let us see. Suppose there is a clay layer. We want to build a structure which is going to apply a load capital P, but this being a critical structure, we would rather like to consolidate this soil by applying a similar load beforehand and afterwards erect the structure. The advantage is when the structure is erected, the soil below would have already undergone consolidation under a load equivalent to what the structure is going to apply. So, we remember our discussion with respect to pre-consolidation and over consolidation. This is precisely that. We are in fact taking advantage of the knowledge of that phenomenon. We are consolidating the soil beforehand and then applying the load, so that any further consolidation, if it takes place, will be minimal and will be normal consolidation. Now, this process of accelerating the consolidation by applying a load beforehand is known as preloading. That is, the clay layer is loaded beforehand, and in order to accelerate this consolidation, we build what are known as sand drains, which are nothing but drains or which are nothing but boreholes filled with some pervious material. We can see this diagram now. The preloading phenomenon usually is in the form of construction of an embankment. So, there is an embankment here. There is a horizontal drainage layer constructed below the embankment in order to provide easy exit for the water, and there are drains provided like this. All these vertical drains, which are filled with pervious materials, permit the flow of water in the radial direction towards them, and their final outgo through the horizontal drainage layer at the top. Now, this embankment load will now be gradually transmitted to the clay layer, and the clay layer will undergo consolidation. And since this embankment is not a critical structure, it is a highly flexible structure and a temporary one, this consolidation can be permitted to take place at a rather rapid rate, and that is why we can afford to use these vertical drains. So, with the help of these so called sand drains, we have accelerated consolidation, which luckily will not affect the embankment in any way, and after the consolidation is over, we can in fact strip off this, remove this embankment and put our own structure on top of this. In fact, this is very frequently used in highly compressible clays, because during the lifetime of the structure we do not want any further compression to take place, number one. Number two, in some clays, some compressible clays, the time required for a certain load increment could be very, very long, which we cannot permit. Now, this shows two different arrangements of these sand drains. Sand drains can be arranged in plan either in a square pattern or in a triangular pattern below the loaded embankment, and accordingly the drainage path capital R will vary for both of them, and it is this value of capital R which will go into the equation which we will be using for calculating capital T R, which we saw in a couple of slides earlier. So, this capital R is related to the spacing of the sand drains and the pattern of arrangement of the sand drains. Based on this, we get capital R, which we can use for getting T R and then U R. So, we can get T R as a function of this R for equal strain condition and corresponding U R using the so called Barron's equation, and this is a graph which represents this. We can also use a lookup table for this purpose. So, in this lecture we had seen a couple of examples, then we have discussed the secondary consolidation phenomenon, and we have seen the importance of radial consolidation. In the next lecture we will continue and see some more examples. Thank you.